Now, let us consider the energy in a dielectric material. How much work is done to store the amount of charge Q and maintain a potential difference V between the plates in a capacitor. That is the energy stored in a dielectric material. So, it is the amount of energy supplied to charge a capacitor, that is the energy stored in the dielectric material. So, how do we find that? Let us consider the differential work done to charge in the process of charging a capacitor, and that will be the potential times the infinitesimal amount of charge, and the potential, if we have a Q charge in the capacitor already, that is Q over C is the potential, times dq, that is the infinitesimal charge that we bring in, that is nothing but V dq. So, the work done to fully charge a capacitor is given as, if there is capital Q charge finally after fully charging it on each plate, then it will be Q over C dq. And if we perform this integral, we will find this to be half Q squared over C. And from the definition of capacitance, we can write this as half C V squared. So, without knowing the total charge that we have put in the capacitor, if we know the capacitance and if we can measure the potential difference between the plates, that is the charging potential actually, that is the maximum potential it can asymptotically reach after getting fully charged, we can still find the energy stored in the capacitor, and that energy is nothing but half times the capacitance times the potential difference squared. This is the amount of energy stored in the capacitor. And let us discuss this in comparison with the electrostatic energy stored in the electric field. So, we have seen that the capacitance in the presence of a dielectric material with relative permittivity epsilon r is epsilon r times its capacitance if there was vacuum in between the plates, and the electrostatic energy in case of electric field is given by epsilon naught over 2 integration over the relevant space E squared d tau. Now, if we have a dielectric filled capacitor, for that we have derived the expression that W can be written as half CV squared, and in the form of its electric field we can write its epsilon naught over 2 integration over epsilon r E squared d tau, and that equals half integral over the displacement vector dot E d tau. So, this is the general expression for energy stored in a dielectric material if the electric field E is developed and there is a displacement vector d. So, if we have a linear dielectric material, we have two expressions at hand, that is W equals epsilon naught over 2 integration over E squared d tau and W equals half integration d dot E d tau. Let us see an example where these two expressions could apparently contradict each other. We have a sphere of radius capital R filled with a dielectric material of dielectric constant epsilon r. We have this sphere, the radius is capital R and it is filled with a material of dielectric relative permittivity epsilon r and it is uniformly embedded with free charge density rho f. Rho f is uniform and is everywhere in the sphere. We have this kind of a situation. What is the energy of this configuration? We are supposed to find the energy of this configuration. How do we do that? First, we need to find the displacement vector as we have done earlier, and we will have to apply Gauss law for that. The expression for displacement vector as a function of position vector would be given as rho f over 3 r vector, and this is valid for r less than capital R, that is inside the sphere, and it would be rho f over 3 r cubed, capital R cubed over small r squared and small r cap. This is outside the sphere. This would be the expression for the displacement vector if we apply Gauss law and calculate it for this configuration. Once we have the displacement vector, we can find the electric field. So, the electric field would be given as this within the sphere and this outside the sphere. With this, we know that in this system, the purely electrostatic energy that we can find is from the first expression, that is integrating over the electric field squared. So, we will find the pure electrostatic energy from this expression. Let us apply this expression first and see what we get. we call it W1 is given as epsilon naught over 2 rho f over 3 epsilon naught epsilon r, this quantity squared, times integration from 0 to capital R, r squared 4 pi r squared dr, plus for the field outside we will write rho f over 3 epsilon naught squared r power 6 integration over r to infinity, everywhere outside the sphere 1 over r power small r power 4 pi r squared dr. This is the electrostatic energy from the first expression, and that turns out to be twice pi over 9 epsilon naught rho f squared r power 5, radius of the sphere powered 5, 1 over 5 epsilon r squared plus 1. Now this is the expression for work done using the first method. Let's box it and let's move on to the second method. The second method is this. We will take the dot product of the displacement vector and the electric field, integrate over it over all space and half it. That will give us the that will give us the energy of the system, energy of basically the same system. So let's take another page, and that way we call it method 2. W2 is given as half rho f over 3 rho f over 3 epsilon naught epsilon r. So the prefactors of d and e we have written here. Then we integrate from 0 to capital R inside the sphere, r squared 4 pi r squared dr, plus outside the sphere the expression would be rho f capital R cubed over 3. This will come from the prefactor of displacement vector, rho f capital R cubed over 3 epsilon naught. This is the prefactor of the electric field. Then integration everywhere outside the sphere, capital R to infinity, 1 over r power 4 pi r squared dr. And if we perform this integral, we will obtain twice pi over 9 epsilon naught rho f squared r power 5 1 over 5 epsilon r plus 1. So this is the expression for W2. Let's box it and let's compare the two expressions that we have obtained. We have from the first method obtained this expression for W1. The only difference with the second expression is this square here, epsilon 1 over 5 epsilon r squared. In the second expression, we do not have any power of this epsilon r. Now, we have epsilon r is greater than 1. It has to be greater than 1 for any value of susceptibility, because it is 1 plus susceptibility, and therefore, W1 is less than W2. What do we mean by that? How could energy be different in different methods? That is not possible, right? Let us analyze what is in W2. W1 is the only electrostatic energy we have calculated from the electric field, and we have derived this earlier, so we are confident about this. Let us see what goes into W2. We start with the uncharged, unpolarized dielectric sphere and bring in the free charge in infinitesimal installments of d cube. So, we have considered this sphere here, and if we consider there is no charge in this and dq installment of charge is brought in here, and this process is repeated until the total charge of this sphere becomes q. We consider something like this kind of a process, and if we consider that the sphere is filled with charge layer by layer, then what happens is, when we have reached radius r prime, let us say this one has radius r prime, up to this it is uniformly charged and outside it is not charged yet in our process of charging the sphere. If we consider this kind of a situation, then the electric field for this configuration would be rho f over 3 epsilon naught epsilon r r vector for r less than r prime. It would be rho f over 3 epsilon naught epsilon r r prime cubed over r squared r cap direction for r prime less than r less than capital R. That means in between r prime and capital R, that region. So, capital R is this much, and the electric field outside the sphere would be rho f over 3 epsilon naught r prime cubed over r squared r cap outside the sphere. This would be the expression for the electric field. Now, the work required to bring the next installment of charge dq and make another shell, that amount of work can be written as dw equals minus dq. So, we are bringing in this charge from infinity, integration over infinity to r capital R e dot dl plus integration r to r prime. We will fix that spherical shell at r prime radius e dot dl. This much work we have to do, and let us perform this integral and find out what it is. So, this dw work is equal to minus dq rho f r prime cubed over 3 epsilon naught integration infinity to capital R 1 over r squared dr plus rho f r prime cubed over 3 epsilon naught epsilon r inside the material from capital R to r prime 1 over r squared dr. This is this integration describes the process of bringing in the charge, and with this consideration, so simplifying this expression, it becomes rho f r prime cubed over 3 epsilon naught 1 over capital R plus 1 over epsilon r 1 over r prime minus 1 over capital R times dq. This is the expression for dw, and this will increase the radius r prime. So, we can write in terms of the increment of the radius r prime this as dq equals rho f times 4 pi r prime square dr prime, and the total work is done in the process of going from r prime equals 0 to r prime equals r. So, if we put dr prime and integrate over it, then the limit of this integration will be from 0 to capital R, and then we can write the expression for work done to perform this process as 4 pi rho f squared over 3 epsilon naught 1 over capital R 1 minus 1 over epsilon r integration from 0 to capital R r prime power 5 dr prime plus no, but this does not end here. This is the factor for this integral plus 1 over epsilon r integration from 0 to capital R r prime power 4 dr prime. This is the total work done, and that gives us twice pi over 9 epsilon naught rho f squared capital R power 5 1 over 5 epsilon r plus 1, and that equals W2. Then we have retrieved W2 from this consideration, while W1 that we have calculated from the electric field, that was the energy stored in the electric field. So, what energy is more in this situation? We have inferred that W1 is less than W2. So, W2 has some more energy stored in the system, and which energy is that? Can we find out the source of this energy? This must be the elastic energy of the system, of the dielectric material. So, we have calculated in the first process the energy from the electric field. So, we have found how much energy is stored in the electric field, but this system under consideration is not only the electric field. We also have the dielectric material, and the dielectric material can store some energy in itself because it gets some polarization, it develops, it gets a little bit deformed elastically, and that stores some energy in it, and the amount of elastic energy would just be W2 minus W1 in this case. So, we can write that W2 minus W1 is the elastic energy, which is twice pi over 45 epsilon naught epsilon r squared rho f squared r power 5 epsilon r minus 1. So, we have just said this. Can we explicitly calculate the elastic energy stored in the material? Let us try doing that. So, we can assume that the dielectric material is a collection of tiny dipoles, each comprising +1 and -1 charge, and a spring constant K is attached to that. That means, we are assuming this kind of a situation. This is plus Q charge and this is minus Q charge, and a spring is attached to this. Where the spring constant is given as K. We can assume this kind of a system and a collection of this representing the dielectric material. In the absence of any electric field, the positive and negative end of these two charges, so they coincide, they fall on each other, and if we assume that one end of each dipole is nailed in its position, let us say this negative charge is fixed, it cannot move, only the positive charge can move. Or we can assume the other way around, that the positive charge is nailed, it cannot move like the nucleus of an atom, only the negative charge cloud can move like the electron cloud of an atom. If we have that kind of a situation, then and the other end is free to respond to the applied electric field. If we have this kind of an understanding, then in the presence of an electric field, the electric force and the spring force would balance each other. So, the spring will get elongated to such an extent where the external electric field applied on this is exactly balanced by this force developed due to the spring. And in that situation, we can write if the distance between these two charges become d at equilibrium, we can write that the by force balancing QE equals KD. Then the electric field vector can be represented as rho f over 3 epsilon naught epsilon r vector, and the dipole moment for this kind of a tiny dipole is given by q times the d vector, this separation vector, and the polarization p can be given as this dipole moment vector over the tiny volume d tau that we have under consideration. Thus, we will have k equals rho f over 3 epsilon naught epsilon r d squared times the polarization magnitude r d tau. That is the spring constant. Infinitesimal work done on the spring in the process of displacement is half k d squared, and that equals rho f divided by 6 epsilon naught epsilon r times the polarization r d tau. So, the total energy in the material coming from all the springs that can be given as rho f over 6 epsilon naught epsilon r integration p r d tau. For a linear dielectric, we know that the polarization can be expressed as, the polarization vector is epsilon naught chi e times the electric field, which is nothing but epsilon naught chi e rho f over 3 epsilon naught epsilon r vector, that equals epsilon r minus 1 times rho f over 3 epsilon r times r vector. Now, if we work out the energy due to all the springs with this expression of polarization, we will find this is equal to rho f over 6 epsilon naught epsilon r minus 1 times rho f over 3 epsilon r 4 pi times integration over 0 to capital R. So, 4 pi comes from theta and phi integration. So, this system is symmetric against theta and phi. We can just write 4 pi for that integral. Only integral over R we have to find out, that is r power 4 dr, and if we calculate this, we will find twice pi over 45 epsilon naught epsilon r squared rho f squared r power 5 epsilon r minus 1. And exactly this was the expression for elastic work done that we were talking about earlier. So, this was the difference between W2 and W1 that we have calculated, and we said that that was the elastic energy stored in the dielectric material itself. So, by working out this simple model that we have two charge centers separated by a spring, and they attract each other by the spring constant, because of the spring constant, because of the spring being there. Under the influence of electric field, they get these two charges get separated, and the spring wants them to bring closer together again, and there is this balance of force, and that stores some energy in this material. With this simple model, we have found out the same expression for the spring energy, collection of all springs in the material, as the difference between W2 and W1 in our earlier work. That means this elastic energy that we have said earlier must be elastic energy is same as the spring energy, and we were correct in understanding that the difference between W2 and W1 was the spring energy and nothing else.